In this session, we are going to look at approximate methods. And in the methods, the first one is successive approximation using the free term. In our previous video, we look at the exact method in finding the solution for an integral equation, such as the Fredholm's integral equation. This method is strictly for Fredholm's integral equation. So let's start by let's consider Fredholm's integral equation of the second kind. In our previous video, we said that this kernel K of st is continuous in a square. R A is less than or equal to S, which is less than or equal to B, comma A is less than or equal to T, which is less than or equal to B. And this free term f of S is also continuous in the fundamental interval AB. So if the kernel and the free term are continuous, that means these two functions are bounded. If they are bounded, then a series, you can use a series to estimate this solution. That is y of s equal to phi naught of s plus lambda phi 1 of s plus lambda square phi 2 of s plus lambda cube phi 3 of s plus plus lambda and phi n of s. So this is a series in the ascending powers of what? Lambda. So we are going to say that this series will estimate the solution for this integral equation. Now, we have our y of t here. If you are saying that this estimate this solution, then let's interchange the s to our t. This implies that let's now we have our y of t to be equal to phi naught of t plus lambda phi 1 of t plus lambda square phi 2 of t plus lambda cube phi 3 of t plus phi lambda n phi n of t. So here, let's substitute this equation into the right side of this equation. So we are going to have our y of s to be equal to f of s plus lambda integral from a to b. Then the kernel K of st in a big bracket, then the whole of this, which is the y of t. Then I have phi naught of t plus lambda phi 1 of t plus lambda square phi 2 of t plus lambda cube phi 3 of t plus plus lambda n phi n of t. Now let's close the bracket, all the t. So this is the resulting equation we are going to have. Now let's expand this equation. Our y of s becomes f of s plus, if we expand this and the kernel and the first term here, then dt. So we're going to have lambda to go from A to B, K of st, phi naught of t dt plus this lambda times this lambda will give me lambda square. So I'm having lambda square integral from A to B, then the kernel K of st phi 1 of t, then dt. Then this lambda times the third term, which will give me lambda cube plus lambda cube integral from A to B, K of st, then phi 2 of t dt plus then this lambda times this, the fourth one, give me lambda to the power 4 integral from A to B, K of st, then phi 3 of t dt plus plus this lambda times this lambda will give me lambda n raised to the power n plus 1. Since this and this is this time this, we need to add the powers. So we're going to have our lambda raised to the power n plus 1 integral from A to B, the same kernel K of st, then phi n of t dt. Now let's compare this equation y of s here to this equation. This equation here. We are comparing this equation to this equation. So comparing this equation to this equation, in the powers of lambda, we can see that phi of s is the same as phi naught of s is the same as f of s. That means that phi naught of s is equal to f of s. And this side, the powers of lambda, this lambda is the power 1, the lambda 2 is raising the power of 1 here. Then phi 1 of s will be equal to the whole of this, which is integral A to B, K of st, phi naught of t dt. The next term, lambda raising the power 2. Then comparing to this side, I'm going to have phi 2 of s to be equal to integral of A to B. Then have my K of st, then phi 1 of t dt. The same thing too applies to this side. We have a lambda cube here. We have a lambda cube here. And so phi 3 of s will be equal to, so lambda cube, so we have an integral from A to B, K of st, phi 2 of t dt. So the n term, that's lambda raising the power n. From this, you could easily see that if phi is, we are having phi of 3, if we are having phi naught, you are having f of s, phi 1, we are having phi 1 of s, we are having what? Phi naught here. Phi 2 of s, we are having what? Phi 1 of what? T here. Then phi 3 of s, we are having what? Phi 2 of what? Phi 2 of t here. Then you could easily generate that our phi n of s will be equal to integral from A to B, K of st, phi n minus 1 dt. dt. So this equations can be generated from this and this. The method of generating this phi n is called method of successive approximation. If I generated this phi n, we call them to be the method of successive approximation. So if anytime you are given a Freudon's integral equation, and anytime you are given a Freudon's integral equation, you can use this method. Phi naught of s, which is equal to f of s, and phi n of s, which is equal to integral from a to b k of st phi n minus 1 of t dt, and the series. And so you can use this in generating your phi's, and this can lead you to what? Generate your series, which is the solution to the integral equation, the approximate solution to the integral equation. So which is given as summation of lambda and phi n of s, where n is equal to 0 to infinity, which is same as writing a phi naught of s plus lambda phi 1 of s plus lambda raised to the power to phi 2 of s, up to this, up to the n term. So this is the series we can generate. Now let's move on to justify our solution, justification of this solution. So justification for the method for justification of the method of successive approximation. When we started, we said that the kernel k of st is continuous in a square. If it is continuous, that means it is bounded. Then let's start by saying that suppose our k of st is bounded by, let's say, a, that is absolute value of k of st is less than a. And we also say that the free term, which is the f of s, is continuous in the fundamental interval, which means that the free term is also what? Bounded. And so and the free term f of s is bounded by m, that is less than m. From this side, now let's consider this relation. We said that phi naught of s equal to f of s, this relation. Now from this side, you can easily see that if I pick absolute of phi naught of s, the same as what? Picking an absolute value of f of s. So absolute value of f of s is what? Less than what? M. So this is here is less than m. And the next one, phi 1 of what? S. Absolute value of phi 1 of s should be equal to integral from a to b, absolute value of k of st, absolute value of phi naught of t dt. Now we said that the kernel is bounded by what? A. And the free term, the phi naught is bounded, phi naught of t is bounded by what? M. This implies that this will be less than our a times m, integral from what? A to b dt. So if you integrate this side, you are going to get what? B minus what? A. So a bracket b minus a. Let's take the next one, which is the phi 2. Phi 2 of s, absolute value of that will give me integral of a to b, absolute value of k s t, then phi 1 of t dt, which will be less than, the kernel is bounded by what? A. So a dot, and this one phi 1 is bounded by what? This am, so I get b minus a, so times a b minus a, b minus a, then the integral sign, integral from what? A to what? B dt, which will be equal to a square, let's say m a minus b, then this integral will give me what? Another a b minus what? A, which will give me equal to what? A square m to ahead b minus what? A square, for the phi of what? Phi 2. And let's move on to the what? Phi 3. In this phi 3, I'm going to have absolute value of phi 3 of s to be equal to integral of what? A to b, absolute value of k of s t, then phi 2 of t, then the t will be less than, we said the kernel is bounded by what? A. So a times the phi 2 is bounded by what? A square m divided b minus a raised to the power of 2. So I'm going to have my a square here, then m to bracket b minus a raised to the power of 2. Then with the integral sign, integral from what? A to b dt. A to b dt. Now we're going to have this one to be equal to, this time this, we're going to have, yes, a square, okay, a square, I mean a square here. I'm going to have here to be a times what? A to be what? A raised to the power what? 3m to bracket what? B minus what? A. Then this give me b minus what? A. So if I multiply this and this using the power 2, so this will give me, which will be equal to a cube m to bracket b minus what? A. So this indices, so here we raise the power what? 3. So the phi 3 of s is bounded by a cube m to bracket b minus a raised to the power what? Cube. From the n term, absolute value of phi n of s should be is equal to integral from a to b, absolute value of k of s t, then phi, absolute value of phi n minus 1 t dt, which will be less than we said the kernel is bounded by an a, so a dot, and the phi n minus 1 of t is bounded by this. If we check this side, we really see that when we are having 5n of 2, we have what? A raised to the power 2m, b minus a raised to the power 2. Then this implies that if here is n minus 1, that means we are going to have a raised to the power n minus 1m. Then b minus what? A raised to the power what? N minus what? 1. Then the integral sign a to what? B dt. So this will be equal to indices. This time this. If you add the powers, you're going to get a raised to the power what? N. Then your m. B minus a n minus 1. If you integrate this, you're going to have b minus what? A. This will become, which is equal to a raised to the power n m b minus what? A. Indices. You add the powers. So we're going to get what? N. We said that from a series y of s, which is equal to phi naught of s plus lambda phi 1 of s plus lambda raised to the power 2 phi 2 of s plus lambda raised to the power 3 phi 3 of s plus dot 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 plus lambda and phi n of s. You can easily see that this will be less than the absolute value of what? Phi naught of what? S plus lambda absolute value of phi 1 of s plus lambda square phi 2 of s plus lambda cube phi 3 of s plus dot 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 plus lambda n phi n of what? S. And we said that our phi naught of s, absolute of phi naught of s, gave us is less than what? M plus, and this lambda phi 1 of what? S is bounded by a bracket b minus what? A, then m plus lambda squared, then this bounded by what? A, this is 2, so I'm going to have what? I'm going to have our a squared into bracket b minus what? A, since here is 2, here becomes what? 2, then times what? Our m plus lambda cube to bracket times what? Oh, this 3. That's like a raised to the power what? 3. A power 3 to bracket b minus what? A raised to the power what? 3, then what? My m plus dot 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 plus, then you are having what? This lambda n. This is bounded by what? Instead of a n, raised to the power n, then what? B minus a raised to the power n times our what? M. If we check this series, you can see that this is a geometric progression. It's a geometric progression with a ratio. The ratio of progression is giving us r is equal to this divided by the first term, lambda of a b minus what? A m divided by what? M. So my here becomes what? Lambda a to bracket what? B minus what? A. So with the ratio of what? Lambda a b minus a, If someone also can choose to take this term divided by this term, you still get the same ratio. That's why we are seeing that it's a geometric progression. For the sequence or the series to converge, the ratio of progression must be less than 1, which implies that lambda a like b minus a is less than 1. So if we solve for lambda, our lambda is less than 1 over a divided by b minus 1. Then if we take, we are going to say that if we pick the absolute value of lambda, should be bounded by 1 over what? A divided by b minus a. And I'm going to say that this series converges for sufficient small absolute value of what? Lambda. Then we can say that this series is a solution to the integral equation. That is the Fredholm's integral equation. So it is an approximate solution to the Fredholm's integral equation.